Welcome and thank you for taking the time to join us for today's webinar, Hydrogen Fuel Technologies. My name is Jocelyn Pazlowski, Modelon's Marketing Director. I'll be the moderator of today's webinar. We will begin with an introduction to Modelon and an overview of Modelon's energy and power system simulation capabilities presented by Stefan Velou, Modelon's Industry Director for Energy and Process. Stefan's presentation will be followed by a live demonstration of replacing an existing natural gas-fired turbine with a sustainable hydrogen gas-fired turbine, which will be presented by Moritz Hubel, Energy System Expert and Team Leader for Solution Services at Modelon. Today's presentation will last roughly 30 minutes, and then we'll have about 10 to 15 minutes available for Q&A at the conclusion of the webinar. The Q&A button is at the bottom of your screen, so please feel free to submit the questions there. And a recording of the webinar will be emailed in the coming days, available on demand. So if you have any questions, feel free to reach out directly to myself or Stefan and Moritz. But without further ado, I will turn the mic over to Stefan.
Thank you, Jocelyn. So welcome everyone. I'd like to start first by introducing Modelon. So over the past 16 years, we've grown to be a global company with offices all around the world. We are headquartered in Lund, Sweden, where I am personally located. But we have established offices in India, Japan, Germany, and also in the US. Our portfolio of customers includes large global enterprises representing aerospace, automotive, energy and power, and also industrial equipment. Our company has been built and developed on the promise of delivering open standard technologies using both Modelica and FMI, the functional mockup interface. We have now a portfolio of 17 Modelica-based libraries that are integrated directly into our new cloud platform, Modelon Impact. So at Modelon, our engineers have worked from the beginning with energy applications, helping customers implementing and deploying model-based workflows for plant design and operation. Modelon Impact allows you to model both conventional and emerging technologies, from the generation of heat or power to their distribution or consumption, covering all physical domains. Modelon Impact is built on a flexible and powerful technology that allows you to model a plant in detail, but also to study its behavior when integrated into a larger system. So Modelon Impact is a comprehensive web-based platform for model-based engineering that facilitates also collaboration within and across organizations. So first, the modeling experts, they can create component models directly in a web browser using an open and high-level modeling language, Modelica. Then energy plant models can then be graphically assembled by drag and drop of those predefined components, either from Modelon or third-party libraries. And at last, control or process engineers can finally implement workflows that use those models to solve for design or operational problems. The models and the workflows can also be deployed to a larger audience, such as sales representative, using web apps. So Modelon Impact in energy covers a wide range of applications. So all from conventional thermal power plants and carbon capture technologies to renewables ranging from biomass, hydro, wind, to various solar energy sources like photovoltaics or concentrating solar power. Modelon Impact offers also models of storage systems that includes battery packs, thermal energy storage, hydrogen, of course, and more advanced systems like pumped heat, or liquid air energy storage. On the distribution side, detailed electrical models of the grid can be used for transient analysis, whereas lower fidelity models are available to solve complex scheduling problems over longer horizons. And this is also valid for the distribution of heat and cool water. We can describe cogeneration plants or heat pumps in detail, but also study the behavior at the district level. So Modelon is continuously monitoring the market trend and understand the value of hydrogen in the decarbonization of the energy sector. We are now working on a comprehensive solution to cover the full hydrogen value chain. So this is the topic of today. So here is an overview of the solution we are currently building in Modelon Impact. So first, models for green hydrogen production by water electrolysis driven by renewables, blue hydrogen production based on steam reforming combined with carbon capture, then models for the storage and the distribution of hydrogen and synthetic fuels in gaseous or liquid form. And finally, models for the last step in the value chain, that is its utilization by either combustion, using fuel cells, or as it is as feedstock in the process and chemical industry. So here are some examples of the value chain you can find in Modelon Impact. So first, in the context of blue hydrogen production, you can find models for steam reforming of methane, including carbon capture processes using either chemical absorption or physical absorption. Concerning the transport and storage of hydrogen, models of liquid hydrogen and of liquefaction plants. And finally, for the utilization, you can find various fuel cell models. And also, this is the topic of today, blending hydrogen in natural gas for the retrofit of combined cycle power plants. So I'm now passing the microphone to Moritz, my colleague, who will be presenting this last use case in a more practical session. So please, Moritz.
Yeah, thank you very much, Stefan. I will take over the screen. Please let me know when you see my impact window.
Yes, I can see it.
Great. So I now have the pleasure to walk you through our Modelon Impact simulation platform. And I will show this on the hydrogen example, as Stefan has mentioned. Just to give you a heads up, I will go through 3 use cases now. The first one will be quite a conventional one, hydrogen cooling in large-scale power generators. And the second short demo, I will show you how to actually use all our well-tested power components with hydrogen. And in the last section or last demo, I will work through the blending process of hydrogen in the combined cycle power plant. So let's look at the Modelon Impact platform. As you can see, the graphical user interface is integrated into my web browser. And all I have to do is to navigate to a server address, as you can see here. So currently I am using a local installation. I have the server running locally on my laptop, but I can also set up on-premises server or even a cloud solution as possible. As you can see here in the lower left corner, these orange boxes, those are the Modelon libraries. And as Stefan has mentioned, we have libraries for different types of industries, as you can see here, ranging from the vehicle dynamics library, which is obviously for automotive application, but also libraries for aerospace and the power industry that I will show today. Now, the good thing about Modelica and the open standard, as you may know, is that we do physics simulation and equation-based modeling here. based on first principles. That means mass balances, heat balances, and so on. So the fundamentals of all these models here are really the same for the different areas of application. So we can actually reuse a large share of models. So also what I'm going to present today for the energy industry can be applicable to aerospace or other industries in the same way as the laws of physics. Obviously, they don't change. It's just a little bit of different abstraction levels and use cases in some of the industries. So what you see up here in the upper left corner, that's my personal workspace. That's where I develop my own models. And in the first example, the generator cooling, I have created a blank space, this white space in the middle. That's the modeling canvas where I'm going to create the model from scratch now. So what you can see on the right-hand side, this panel here, that's where we configure the model and add the properties. This is blank now. I have just added some documentation to illustrate the use case, the first one I'm going to show you. So as I mentioned earlier, I will investigate the thermal effects of a large-scale conventional generator. This device is used to convert mechanical energy or power from a rotor into electrical power. And as this process is non-ideal, this will cause heat generation. And in order to balance that heat and and avoid overheating of the rotor, this rotor needs to be cooled typically, and we use gas for that. So as for every model, we need to do some abstraction here. And I have created this little bit of ugly graphic here, but that should not be our typical design. It's just to illustrate that really users can edit the documentation here, adding pictures, adding fonts as they like. So this thermal effects for the cooling itself will be represented by a mass flow source here on the left side, the blue circle that is used to feed in the gas stream. Then the gas will pass through this component called distributed pipe here and transfer heat or take up heat from the metal surface of the rotor. The conversion process or the heat loss is just represented by a simple heat source. And then there's a pressure boundary at the back end of the rotor where the flow is going through. So now I will build this model from scratch. I have created this empty experiment here, and I can just show you where I will take these components. So this is this is our base library, the Modelon library package here, and that contains a sub package called thermofluid. And that's what we can use for very fundamental physics. In order to speed up that process a little bit, I have these favorite sections here. So I just marked the components I'm going to use right now. But basically, that's the same as if I drag them from the libraries. So first, I will drag in this mass flow source, the pressure boundary, that pipe in between, then the heat flow source, that is environment Q by default. I can also flip that component to make it look nicer, and then I can just connect. If I do the fluid connections here, Impact will automatically show me what ports I can connect to. So if, for example, I cannot connect to the heat port. So here the fluid is now coming into the pipes, and I will connect it to the back pressure as well. So for the heat components, you see this little red box here. I can connect them, but they're usually vectorized port. I can discretize the pipe in the actual direction, or also some in the radial direction. If I look at the parameter inputs of this model, I can again expand my right panel here. You see the documentation. I won't read that right now, but I can set parameters for this component. I will just use one element of discretization and set a reasonable heat flow for this generator. I can also rename the component here as I like. So as it's the heat loss, I will call it just loss. Then for the actual metal that is going to heat up, I need to set up some parameters in the same way. Here you can see the discretizations by default 2. I will change that to 1, and I will set some parameters for specifying the metal properties, so the specific heat capacity, for example, and heat conduction resistance. I also need to give it some default mass value, just something reasonable, and then I can connect them here, and similar to the fluid connector, but now we have a vectorized connector, so Impact lets me select if I want to connect certain elements or the entire vector. Doesn't really make a difference here as we only have one element. So for the pipe itself, that's the most interesting component maybe here from that example. We see a lot of options and inputs here, so we need to specify the dimensions. For example, I choose now 10 parallel pipes and have a length of 5 meters each and diameter of 10 centimeters. What we of course want to do is heat transfer. So I need to enable that. If it's not enabled, it's quite simple to run it. And then I can select one of our predefined heat transfer correlations. There's a lot here. I will just, for this very simple demo, select a constant one. Yeah, and that's about it. So I can connect again the heat port here and select the options. What I didn't do so far is specify this mass flow boundary. So the default is I don't send any mass flow. I will change that to 10. And for our first scenario, I will create the reference case. So I'm using dry air. I could also select a variety of other media models, as I will show you in a minute when I will switch over to hydrogen actually. So once I press this play button here, the engine behind Modelon Impact, which is the Optimica compiler toolkit, will convert this nice graphical representation of our model into something that my computer likes to solve. This process can take a couple of seconds, but now as you see, it's finished and it will automatically pop up my result here in the last part of the workflow. I now simulated with the default settings. I will do that again, maybe to simulate for 10 seconds. That's the one I wanted to do. And I see that went much quicker than the first one. So now that I have finished the simulation, I can investigate every single component here. So what I was specifically interested in here is the temperature of the rotor. And as you can see in this scenario, we didn't care about the initial value, so we just initialized with ambient conditions. So we have some transient response here, but after a couple of seconds, and that's why I changed it to 10, we will see an equilibrium state with that specific amount of heat loss and that fluid flow that is extracting the heat. I will also rename that result to compare it later. Appropriate name, I would say. And yeah, let's jump into the actual hydrogen cooling. So hydrogen cooling for large scale generators is something that is not new. So that has been developed and also used since the 1930s. So it's a pretty well-known technology in the industry, and that's quite similar to Modelon's products. So we have developed these power components for a long time. And as you will see, we can just replace the medium, and we've had hydrogen also for a very, very long time. So that's tested well from all our media models. I can just select hydrogen here. It's not too many, that's why I need to filter actually. And I see a lot of mixtures of hydrogen, gases, two-phase hydrogen, and so on. So for the next step, I just want to use a real gas model of hydrogen. And I will, in the next step, show you how to gradually increase the hydrogen content. Now again, I forgot one thing here. I just replaced it on one of the components, and in order to get it passing through all the components, I need to push this button here, and that will allow to propagate the media model automatically to my entire network. And yeah, again, I need to compile that model again, because now I changed the structure. If I only change parameters, I don't always need to recompile. Here I'm also using my laptop, as you can imagine, on a workstation or on the server that will run much quicker. But it is possible, of course, to run also large power plants model, as I will show you, on really simple hardware. But that's generally one of the main advantages also of Modelon, that when you use a cloud or a server installation, you don't need any specific hardware requirements on your end device. So what we see here is that the usage of hydrogen has actually reduced the average temperature of the rotor by roughly 10 degrees. So that's again a very well-known good effect, and that's due to the fact that the heat capacity of the hydrogen gas is very large. So it's about 14 times higher than the one of air. And now next, I have prepared a little experiment here that I will run now. And what I want to show you is that we can gradually increase the content of hydrogen. So I have added this top level parameter to my model, which is the mass share of hydrogen. And on my mass flow boundary, I can just have this flag here that I will use the composition as an input. This will automatically generate this connector here and allows me to connect this source of any data here. I can do that for mass flow or temperature in a similar way. Otherwise, I would just use the constant parameters. And here I've specified the vector now, composing the fluid from nitrogen and hydrogen. And I want to set this experiment now. Take a second. I want to show you how to use now Modelon Impact to do multiple simulations at once. So what I'm going to do is I change the hydrogen content from 0 to 1, which means 100%. And I will do that in 10 steps. And that's the operator we use to that. And in order to compare the effect with something else, I will show you how to do that with the same way. So I will increase the mass flow from 1 kilogram per second to 10 kilogram per second, and do that in 10 simulations as well. Now there's 100 experiments that I've just created, and the engine again will solve those experiments. Increasing the hydrogen content from 0 to 100% and increasing the flow. As the simulation finishes, we can again have a look on the result, which will pop up here automatically. So I've just created this new one, and there's 100 different test cases now included. And we can again browse that and check the average temperature of that medium. So plot that here. As you see, that goes up to 326 degrees, which is pretty hot. So the last case was with no hydrogen cooling and low mass flow. And using the 3D animation plot, we can actually investigate the effects of the hydrogen and the mass flow. So I can draw that a little bit larger here. See on that axis how we increase the hydrogen content from 0 to 1, which means again 100%. And on that axis here, we increase the cooling flow. And on the vertical axis, you'll see the resulting average temperature of the component. And as you can see, again, the hydrogen increasing the hydrogen share in our cooling has a similar effect as increasing the actual mass flow. So that's why people have been using that for a long time. Also, of course, it may not be possible to pass a large mass flow through the generator, because due to the small gaps, you want to have them small to make them efficient, and there's a trade-off between the pressure loss. So it's pretty obvious to use hydrogen for large generators, larger than, say, 300 megawatts. So that was a fundamental introduction. Now I've prepared some more presentation here. So this is how we can use two-phase hydrogen models with our existing components. And as I mentioned, so this was the Modelon base library I introduced the first, and then we have this thermal power library. And in there's actually a large package for two-phase media component models that will be that you can use with two-phase media, including different types of tanks, heat exchangers, turbo machineries, pipes, valves, and all that stuff that you need to represent power cycles, liquefaction, and so on. So in this example, I've just connected two tanks here. So this is two-phase tanks that has been used with water, or for example CO2 in the power industry for a long time. And I have again just switched the media model here. And what this experiment is supposed to show, I will open the valve here of one of the tanks, and after 5 seconds, and then the hydrogen will expand, and so I pass it through a pipe that is connected to ambient conditions. It will heat up a little bit, so I can run this experiment. There's a little bit more physics in here, but as I see, it's quite fast. And then we can have a look on the results that should be animated in this logarithmic pressure enthalpy diagram. So we can see and illustrate the process as we go through the time here. So we see that we start at the equilibrium between the vapor and the two-phase region in the tank at around 6 bar, and then we expand in this valve. And after that, we will evaporate the hydrogen. So that's again just a small example here. So in the last step, I have used these hydrogen tanks to integrate hydrogen into our combined cycle power plant that Stefan has mentioned. So I can increase my screen here by removing the panels, and I will see the full scope of that model. So you will recognize again that hydrogen tank that I've just shown. And here you will find one of our system example that comes with the thermal power library. And that is the comprehensive model of a combined cycle power plant. You will find the gas turbine here, including the compressor, the combustion chamber, and the gas turbine, and the heat recovery steam generator that uses that hot flue gas to drive the steam cycle, so the Rankine cycle. That is also a model that has been used for studying carbon capture, but I won't go into details on that here. So what I want to show you, and as the simulation is obviously more complex, I have prepared a result for that before this demo. So we will see the same type of result as for the other examples. Just this model took roughly 10 minutes to run on my machine. And we can see what happens here. So I will open that hydrogen valve in my scenario at a time of 5,000 seconds until 8,000 seconds. And this will mix hydrogen into my fuel stream. And as the power is controlled, this will decrease the mass flow, and the overall power should remain constant. We can check on that. If we, for example, look at the gas turbine power here, we can verify that that's true. So the gas turbine runs at a nominal power of 360 megawatt, so large scale. And then we see some control thing here that happens when we change the hydrogen content. So that's a disturbance, but after a short time, the controller managed to balance the load again, and it's again 360 megawatt. So we can now also investigate the hydrogen share. So what I did here was I have increased the hydrogen from 0 in the first 5,000 seconds of the scenario to 35 mass%. And due to the fact that hydrogen has an extremely high heating value, it's actually 3 times higher than methane, for example, that 35% corresponds to already about 70% of firing power from hydrogen. So pretty high share already. So we should see that at the same time as we increase the hydrogen, we will just decrease the methane, which I can confirm by showing that graph here. So there's some other trace elements in the natural gas, so that's why it's not 1 in the beginning, but we just reduced the methane and replaced that with hydrogen. So what we can now do is to investigate our entire plant, really. So that's a typical use case in the future, of course, as the natural gas grids, they will get more and more hydrogen from electrolyzers, and this may be something that not even on a retrofit really, but during operation really of existing plants that can happen or will happen to increase the hydrogen content in the grid. So we can, for example, look at the exhaust of that gas turbine and see what's coming out there. So one of the main effects is that the composition of the fuel gas will change, flue gas will change. So here I plotted just the water content in brown and the CO2 content in purple. So as you can see, when I increase my hydrogen content, I will have a significant reduction of CO2, which is the good point. So that's what we actually want to achieve with all the hydrogen economy. So that worked out, that's fine. But we can also see what will be the challenge of that increasing water content in the flue gas. So we can now also browse into the component. I can just open that in a new tab in my browser. That's also a way of working. If you work, for example, with multiple monitors, you can just detach that tab from your window and have them on separate screens open. I don't want to go into all details, just here so show you what's under this icon of the gas turbine and study the effects here. As I have promised to you, there's a compressor and the combustion chamber and the turbine that's really running under that icon. And we can, for example, see the effects on the outlet of the gas turbine and, for example, see that while we increase the hydrogen content, we'll have a decrease in mass flow of the flue gas and also decrease of the exhaust temperature. So that may lead us to the assumption that also maybe the power of the steam cycle will be reduced. We have less mass flow and lower temperature. But then if we look at that steam turbine power, we will, for example, find that this actually increases from 156 megawatts in that case to 170 megawatts. And the reason for that being quite similar as the first demo. So the water in comparison to the carbon has a much higher heat capacity. So even though the temperatures of the flue gas and the mass flow decreases, we actually have more power available in the heat recovery steam generator. And that's just one of the challenges that you need to face when you want to retrofit or even gradually increase the hydrogen content in an existing plant. You will need to check the design of your heat recovery steam generator. So here you can see what's under that model. So there's a lot of heat exchangers and I, of course, don't have the time to go into every detail, but with this model now you can study the effects. So what's the pressure, what's the water content, what's the humidity in all of these heat exchangers. And so there may be challenges designing the spray attemperator valves as you have more energy now in the HRSG. As you mentioned, you may have difficulties with the dew point and the humidity in the flue gas as you increase the water content. So unfortunately, we haven't solved these challenges, but we have the tools, we would say, to solve these challenges. So it is quite easy to build combined cycle power plants here. We have the examples ready and then can go ahead and study the effects dependent on the question. But I would say that's a good starting point. So yeah, again, there was just one very brief overview, but be happy to have you on an evaluation or working with you on more use cases here. So I'll hand over to Stefan or Jocelyn again. Thank you.
Yep, thank you. And I'm actually going to turn the mic back to Stefan for our final comment.
Let me know if you see my screen now. Can you see my screen?
Yeah.
Okay. So yeah, thanks, Maurice, for this insightful demo. Before we close the webinar, I'd like to give you a glimpse into our ongoing and upcoming activities in the field of hydrogen. So we are currently working on increasing further the fidelity level of our fuel cell models. So we have a fuel cell library. It contains different types of fuel cell models, but we are working on improving the details of the models. We're also building our first alkaline electrolyzer model and also solutions for the storage and the supply systems. It's also in the near-term plan to start looking at the production of synthetic fuels like ammonia. So stay tuned. Thank you for listening.